industry panel session. The name is the TRON Project 40 Years of Innovation. I'm Kyoshi Ueda, the chair of this industry program session, panel session. And I would like to introduce the moderator of this session, the Professor Takeshi Yashiro. He's currently a professor at the Interfaculty Interactive Information Studies, Toyo University, but mainly he engaged in the real-time operating system based on the TRON architecture. And he has played the leading role of developing a new platform based on the TRON. So please use session. Yes.
Okay, thank you very much for your introduction, Ueda-sensei. Now I would like to start the session. And hello, ladies and gentlemen. Thank you very much for joining this industry session. And this session is entitled The TRON Project, 40 Years of Innovation and Future Horizons. And we would like to introduce to you what we have done in 40 years and what we pursue for the future of computer systems based on IoT. And before we begin this session, we would like to introduce the panel members for this today. I am Takeshi Yashiro, the moderator of this session, and I'm a professor at the faculty of INIAD, Toyo University, and my research interest is on IoT and embedded systems. And I have been involved in developing the TRON real-time operating systems, as well as IoT aggregator, which is the cloud platform for the IoT. And I have been working for the TRON project for since when I was 22. So I am 42 now, so half of my life is with the TRON project. So thank you very much for attending this session. And I look forward to discussing with you on the future of computers with you and the panelists. And let me introduce to you the Professor Sakamura, the person on the middle. And he's the founder and the leader of TRON project and has contributed to embedded systems and the IoT. And he's not attending here real time, but gave me a video message to us. So we will play that later in the session. And today we have Dr. Hiroki Hihara from NEC Space Technologies. And now he's attending remotely via Zoom. Could you introduce yourself to audience, Hihara-san? Maybe we can switch. Can you switch to Zoom? Oh, okay. Then I would like to start. And Dr. Hiroki Hihara will be attending later, I think. Okay, so firstly, we would like to thank you all for having a chance to introduce our TRON project in ICCE2025. And Professor Ken Sakamura, the founder of TRON project, gave us a message for audiences here today. So could you play that video message? Thank you.
Stands for the Real-Time Operating System Nucleus, and it is a computer architecture project for embedded systems that began in 1984. This project primarily focused on designing operating systems and adhered to the principle of open architecture. By openly sharing its designs, the project aimed to make its innovations accessible to people worldwide who are interested in embedded computing. This initiative has been led by the TRON Forum, a non-profit organization, and it has operated entirely through private efforts. Over the past 40 years, the project has been supported by donations from approximately 1,000 organizations globally. In the past, companies like IBM, Xerox, and Motorola joined the effort, and today, companies such as Microsoft and Google have also participated. In 1984, the era of microprocessors was beginning to have a significant impact on society, with personal computers like IBM PCs starting to emerge. Microprocessors were primarily used for two purposes: information processing and industrial applications. TRON project placed particular emphasis on industrial applications, especially controlling physical objects. Moreover, anticipating a future where these edge nodes would be interconnected, the project proposed an architecture known as HFDS, Highly Functioning Distributed System, supporting numerous middleware technologies designed for networking. In today's terminology, we can say this was a forerunner of the Internet of Things, IoT. One of the first accomplishments of the TRON project was the development of a real-time operating system, RTOS. This resulted in the creation of ITRON, Industrial Tron, which has been widely adopted globally. It played a crucial role, particularly in Asia, in industries such as consumer electronics and automotive manufacturing. For example, ITRON was used in the world's first digital camera, the Casio QB10, as well as in Toyota's engine control systems and gaming devices. The success of the TRON project stems from its adherence to the principle of open architecture. By sharing its design philosophy, the project enabled collaboration among numerous companies and researchers, facilitating the development of innovative technologies. TRON helped Japan secure a global position in industries such as home electronics and automotive manufacturing. Moreover, as Asia became the factory of the world, TRON significantly contributed to the strengthening of industrial capabilities in Asian countries. In addition, Japan has actively utilized TRON technologies in its peaceful space exploration efforts. For instance, the Hayabusa project, which successfully returned samples from an asteroid, leveraged TRON technologies, showcasing their versatility across various fields, including aerospace. In recent years, the TRON project has intensified its focus on artificial intelligence, AI, targeting the unique requirements of embedded systems development. These include priority-based scheduling for code generation, context generation, simulation, and debugging within virtual IoT environments. These innovations are foundational for shaping the next generation of IoT. The project achieved significant recognition in 2023 when the TRON Real-Time OS family was designated as an IEEE milestone. In 2024, another milestone was achieved when TRON Intelligent House, developed in 1989 as part of the HFTS initiative, was recognized as the world's first intelligent home. This house integrated hundreds of computing nodes, embodying the concept of a smart home over 30 years ahead of its time. The fact that TRON has been honored with IEEE milestones for both its foundational RTOS technology and its application in smart home architecture highlights the project's foresight. This recognition reaffirms the societal and technological importance of the TRON project and validates decades of dedicated effort. I would also like to take this opportunity to express our deepest gratitude to IEEE for the tremendous support it has provided over the years. The IEEE Consumer Technology Society has been a longtime sponsor of the TRON Symposium, fostering its growth. Additionally, IEEE recognized the TRON RTOS as the basis for the IEEE 2050-2018 standard, significantly advancing the standardization of RTOS technology. Furthermore, in 2023, I was deeply honored to receive the IEEE Masaru Ibuka Consumer Technology Award. This recognition for my leadership in the development of open and free embedded operating systems reinforces the importance of TRON's contributions to consumer electronics worldwide. Moreover, IEEE facilitated the dissemination of TRON-related knowledge by publishing proceedings of TRON Symposium as a sister association. These initiatives have played a pivotal role in enabling the TRON project to achieve its current prominence. Today, the TRON project continues to evolve, integrating AI and advanced communication technologies to make further contributions to fields such as consumer electronics and industrial equipment. It also remains committed to passing on its vision and achievements to the next generation of engineers and researchers. Thank you for your interest in the TRON project. We look forward to continuing our efforts to drive future technological innovations.
Thank you very much, Professor Sakamura, and for the staff that played this video. So from here, we would like to move on to the details of TRON project. And first of all, let me explain the IEEE milestone. An IEEE milestone is a recognition program for historical achievements in the fields of electricity, electronics, and information technology. And in general, receiving IEEE milestone is very difficult in that IEEE only gives them to those who change the history of computers. Apparently, changing the history of computers is very difficult, so it is very difficult to receive. And regardless of this difficulty, TRON project has received IEEE milestones for 2 consecutive years. In 2023, TRON real-time operating system family has received IEEE milestone. And in the next year, 2024, the pioneering TRON Intelligent House has received the IEEE milestone. So why was that possible? And it is because TRON project has continued to pave way for development of embedded systems and IoT as pioneer. And however, the name TRON might not be popular to public compared to Windows and etc. This is because the information on embedded systems are often hidden inside manufacturers, and they're not often disclosed to public. For example, if you buy some electronic gadget in some store or something, and it does not say TRON inside, right? For example, if you buy a PC, sticker like a Windows inside or Intel inside is put, but TRON inside is not put on embedded devices. Hence, the name of TRON is not much known to the general public, but what is important is that they're used in embedded devices and now regarded as an embedded real-time operating system standard for the IoT edge nodes. And from here, let me first go through the 40 years of TRON project, what we think and what we pursue. And first, let me start by introducing to you the very beginning of TRON project in 1980s. And actually, I was born in 1982, so I was only 2 years old when the project started. Still, by reviewing the history of TRON project, I was deeply impressed by what TRON project has aimed and done. And I would like to share it with you here today. And TRON project was started in 1984 when computer technologies were evolving rapidly. At that time, the personal computers were born, like Apple II computers and IBM PC in 1981. And however, the evolution of computer technologies tend to be short-sighted, as we often develop technologies that we need now. I often do so, so it is natural. But when thinking of important computer technologies like computers, and this may not take us to an optimal solution. And as the computers are complex systems and are incrementally developing on the existing ones, decision affects the future for long. One of such example is the most expensive 1-byte mistake stated by cHUB in 2011. And as you know, the programming language C represents string as array of characters terminated by no character, which is a magical byte, not by the character array in addition to length format, right? And this decision in 1970s was done to save 1-byte memory. And by using the magical byte, it only consumes 1 byte. But if we use the length format, the length uses 2 bytes, so it can reduce the amount of 1 byte of memory to be used. However, this decision still suffers us in many respects, and it includes the deterioration of performance and optimization like we do in string concatenation, and there are security issues caused by this decision. And such mistakes in computer science is everywhere, like use of backslash character for file separator, or initial choice of Unicode to represent word character as 16-bit integer. So in this regard, TRON project was established in 1984 to guide computers to guide evolution of computers to a correct path in a scale of decades. And it was started with a clear vision to illustrate the grand design of future computers. And let me show you the early sketches from the TRON project in 1982, when I was born, actually. And these figures are drawn by Professor Sakamura, who gave us the video message. In 1982, the laptop computers were very thick and heavy, but the design of computers here resembles the one we use now. And these are the proof of concept design of TRON computers. As the keyboard is a very important interface for human-machine collaboration, the placement of key tops are optimized to maximize input efficiency and reducing fatigue of human fingers and arms. And there's several figures, and the figures on the right is the design of an intelligent smart city in 1980s. And thank you. And you can find the idea of smart building and smart cities in the design in 1980s. And in order to guide computer technologies to a correct path, TRON project has been started with a clear vision of the future computers. Among them, we have two core concepts that we refer to as TRON philosophy. One is open architecture, and the other is highly functionally distributed system. Let me explain these one by one. And the first one, open architecture, is a paradigm where the foundation of computer technologies shall be kept free and public, where derivative products can be built. This is considered, for example, if use of English language for communication that we use now is billed $5 per use, it will have limited global communication, right? So the similar thing can be said on the core computer technologies. So the derivative products can be, of course, built, but the core technology shall be kept open, like Internet. And the main focus is on design and compatibility, unlike open source. So it is different from open source in that derivative products can be closed to assist the marketing and selling the products. And another is the highly functionally distributed system, whose idea where the computers would become very cheap and distributed everywhere to support our activities. And similar idea can be found in ubiquitous computing presented by Mark Weiser in 1991. And in academic paper published in 1987, Ken Sakamura has proposed the idea of highly functionally distributed system in 1987 in English. And this is 4 years before the computer for the 21st century by Mark Weiser, which presented the basic idea of ubiquitous computing in his publishing. And this is the diagram explaining the highly functional distributed system in the paper, which we now refer to as the Internet of Things. And in this paper, the concept of highly functional distributed system is explained. Every object around us, like here, for example, here, intelligent lighting, intelligent ceiling, and intelligent air supply, and intelligent sensors, etc. And they all have computers embedded and are all connected to an open-ended network. We have Internet now, so it is Internet. And these intelligent objects collaborate with each other to form an optimal environment for us. This is the idea of highly functional distributed system. And as the idea of highly functional distributed system requires distributed system with heterogeneous computing systems, realization of this is not that simple. So in this regard, TRON defined several sub-projects to be used as key factors for highly functionally distributed system. They include iTRON, cTRON, vTRON, and many others. And they are used to realize the highly functionally distributed in our computing environment. For here, iTRON is used, and here the vTRON is used. And firstly, iTRON is a real-time operating system specification for embedded systems, which is one of the most important technologies in the TRON project. And it is used to realize intelligent objects in highly functionally distributed system, and it is widely accepted as one of the standards in consumer electronics today. For instance, some of you may have a Nintendo Switch at your house, and the Joy-Con for the Nintendo Switch is implemented with micro iTRON inside. And currently, iTRON and micro iTRON-based operating systems are regarded as one of the standards in embedded real-time operating systems. And for instance, all of the embedded products here uses micro iTRON-based operating systems. For example, car navigation system from Bosch, or automobile crown from Toyota, and the digital camera from Samsung, and also the digital piano from Yamaha. All of these uses micro T kernel or micro iTRON, TRON-based operating system at its core. And the reason why TRON real-time operating systems are accepted is the use of real-time operating system as its core. And for example, it is necessary for intelligent objects equipped with sensors and actuators. And when computers are connected physically to the real world, it can be dangerous if hard real-time constraints are not met. For example, imagine a situation where we want to control a drone. And if a posture of a drone is tilted, for example, by turbulence, and recovering from it to a normal position is necessary. Otherwise, the drone will drop and fall and crash. So such operations need to be handled within the hard real-time constraints to assure safety and correct operations for the product. So TRON operating system has chose real-time operating system as its core. And such examples include response performance of automobiles, brakes, and temperature control of gas water heaters, and posture control of drones. And that kind of computer systems that affects the physical environment need to use a real-time operating system at its core. And cTRON, the communication and central TRON, is a real-time operating system for high availability for central computers. And the performance of context switch between tasks was 10 times faster than real-time Unix operating system at that time. Please see table 1, some of the parts I translated to English. And for the task switch transition here, the real-time Unix required 1,500 microseconds, while cTRON only consumed 137 microseconds for corresponding operations. So we can say that the cTRON operating system is very quick and fast. And because of this, it was used practically in important central computers like telephone exchange systems, mainly in the Asia region like Japan. And the BTRON, Business TRON, is a real-time operating system for personal computers with graphical user interface. As this is a personal computer operating system, it can be considered a competitor for MS-DOS, Windows, and Mac OS at the time. And although the target was quite similar to current desktop operating system, its design was quite unique and was different from any other operating systems. Let me explain that using the demo. The difference of the BTRON from any other personal computer platform lies in network structured file system. Usually, file system in Unix-based operating system or Windows is a hierarchical structure that forms a tree, like on the left. For example, if you use Windows or Mac OS, your files are put on some folders, and folders can input folders. So basically, the files are put on inside the folders. However, the design of BTRON is very different in that the BTRON adopts network structure file system on the right, like this. And the network structure is similar to the hypertext document. If you write a hypertext document like HTML, you can imagine that. And this design is very peculiar in that files can be embedded within files, not only folders, and still refer from other files. So let me explain using the demo. Let me show you a demonstration of using BTRON. Here we have one paper PDF document in a folder. Let's put a new document in a cabinet. Yeah, I have put a new word processor document here, survey report. And by double-clicking the document can be opened and edited. Here I'm putting research objective or something, and related work. And when serving the related work, we want to put the PDF documents here, right? And it is possible in BTRON. So BTRON operating system allows files to be included within files. So we have put the PDF document file here, and it can be double-clicked to open. Yeah. And what is interesting here is that we can also put files within PDF files like this. The word processor files put on PDF. And we can put a memorandum here. Here, U2DA is a U-code distributed database or something. And such documents can be put here. And still, additionally, another document can be added within PDF files, and the file can be made open to show its contents within the documentation. So it's a very unique system that allows collaboration of many different applications within the same file. Yeah, like this. And it can be double-clicked to open. So it is the demonstration of BTRON operating system, which is very different. And BTRON is made to serve as a user interface to highly functional distributed system in communicating machines. And here we can, this is a screenshot of an old TRON system. And here we can see lighting and air conditioner and also the volume for the audio. And these are all the abstraction of IT devices as TRON files. The similar idea can be found on the device files in Unix, but is extended to allow other devices with user interface. So this is the idea of how the TRON is implemented for highly functionally distributed system. And as the computer technology evolves, the problem of digital divide, where persons with disabilities and so on may be left behind in computer technologies. And TRON Project has been aware of this problem from the beginning and started Enableware project in 1988. The word enableware apparently is a combination of enable and where, and thus aim to support persons with disabilities and so on with computer technologies to enable their ability. And this is an example experiment conducted in a university campus. Let me show you the video.
This is the campus of the University of Tokyo. We guide the visually handicapped by using tags embedded in tiles on the ground from the main gate. The visually impaired carries a cane with a reader at the tip to obtain the audio guidance.
It is to the left. Go right at the fork 5 meters ahead. Fork. Go right. You are near the south. You have passed the fork. Yasuda Auditorium is diagonally left at your back. Take the fork 5 meters ahead to the left. Fork. Go left. You are near the south side of the Faculty of Engineering Building 11. Yasuda Auditorium is approximately 260 meters away. To the left is Intellectual Promenade, an agora which was created to mark the 130th anniversary of the university's foundation. In this area there are 2 bronze statues of foreign instructors from the time of founding. The statue in front of Faculty of Engineering Building 11 is Josiah Condor.
The audio explanation of the neighborhood is at the request of the visually impaired. They say it is boring to keep walking without knowing what is around them.
So this is an example of Enableware project in the early stages of TRON project. And in order to evaluate the effectiveness of intelligent house idea presented in the highly functionally distributed system, TRON Intelligent House was first built in 1989, and it is considered ultimately became the world's first smart house. And these are the pictures of the TRON Intelligent House built in 1989. And household facilities like toilets are connected to the internet and provide smart service to the residents. In this example, a toilet is connected to the internet and provides healthcare information, healthcare monitoring to the service to the residents. In the kitchen, as an example, it includes a monitor for showing the recipe of the cuisines. And the upper 2 figures shows the controlling system of the house. At that time, the networking technology was not sophisticated as we have now, so it needed a bunch of serial cables like this to realize TRON House as a proof of concept, intelligent building in reality. And let me show you some parts of the video explaining TRON Intelligent House. And actually, this video is on YouTube and it has approximately about 8 minutes in length, so I cannot show you all here. So if you're interested, please check our YouTube page to view the full contents.
The first TRON Intelligent House was built in Tokyo back in 1989. Let's take a look at some of the features of this pioneering house. The floor space was 333 square meters. Basic components of the house, such as windows, were embedded with computers, sensors, and actuators. The house was built to realize the house of the future, when such components in the house would be connected via communication network. The design of the computer system and the architecture of the house was done by Ken Sakamura.
Okay, so it's too long, so let me stop here. So it's on YouTube, so please check if you're interested. And this is what TRON Project has achieved in the early days. From here, we would like to introduce to you the state-of-the-art TRON Project and its technologies. In 2020s, TRON Project has redefined the TRON standards to bring out the power of state-of-the-art microprocessors, network technologies like IPv6 Internet, and etc. And they include T-kernel operating systems, T2EX, which is a T-kernel 2.0 extension, and also IoT engine and UCode. Let me explain them one by one. And from the time that TRON Project has started, the technology has evolved much. And for instance, the first personal computer in 1970s and 1980s were initially 8-bit computers, and then 16-bit. And now we generally use 64-bit processors and accelerators like GPU on personal computers. So embedded technology also advanced a lot since ITRON in 1987. So hence, the evolution of operating systems need to be kept to make the full out of the state-of-the-art computing technologies. In that respect, T-kernel is the state-of-the-art ITRON for the 21st century, and it is designed based on the ITRON, industrial proven for long since 1980s, but with major revision to be adopted for computing technology of the 21st century. And when we created T-kernel operating system, the microprocessors for embedded devices became very rich compared to the beginning of the TRON project. So because of this, we have made T-kernel open source in addition to open architecture. And the reference source code for T-kernel is distributed for free, and anyone can use it, alter them, and sell them. And by doing so, T-kernel has gained higher compatibility among different versions of T-kernel and implementations of T-kernel. And the original source code defines the specification with no ambiguity, so higher level of compatibility among T-kernel operating system is realized. And in addition to that, higher compatibility among T-kernel systems assure middleware and application may be reusable. If we want to make very complex embedded systems, the code size became very large. So we need to use a middleware for implementing application systems in some informational gadgets. And in that case, file system and other image processing and that kind of libraries are needed. But with higher compatibility, the libraries and middlewares can be shared across multiple T-kernel implementations. So the middleware and applications made reusable. And currently, ITRON and T-kernel are accepted as the most commonly used real-time operating system for embedded systems. And due to the successful concept and cooperation among the members of the TRON project, the ITRON and T-kernel is now one of the de facto standards in the world of our real-time operating system. And according to a survey, ITRON and T-kernel has had the topmost share for 18 consecutive years. So it is one of the most commonly used operating system in this world. And recent advances in microcontroller technologies led to multi-core processors and high performance on embedded systems. And thus we provided 2 versions of T-kernel supporting multi-core and multi-processors. And one version showing on the left is SMP T-kernel, which is a symmetric multiprocessing version. And we also have a symmetric multiprocessing version called AMP T-kernel, and both can be used to utilize the multi-core and multiprocessor computers for embedded systems. And in order to help manufacturers to create high-end embedded products with ease, we provide T2EX, which is T-kernel 2.0 extension. And it provides file systems, program loading, TCP/IP, and memory protection, all of which is illustrated here. And however, the virtualization like processes are not provided as T2EX is for embedded system. And for example, imagine a case where you want to implement a digital camera, and digital camera need to store pictures taken to SD cards, and that would require a file system. And T2EX provides such functionalities which were not standardized in ITRON at its core. And we also have T-kernel operating system variant for small-scale embedded devices, and it is called micro T-kernel, and it corresponds to micro ITRON for ITRON, and it can be run on 4 kilobytes of RAM with minimum configuration. So if you're using PC now, your PC is like 4 gigabytes of memory, right? However, the micro T kernel only uses 4 kilobytes, not even megabytes. So we can say that the real-time operating system for embedded system is very small, and the micro T kernel implementation is kept very small. And T kernel operating systems are downloaded and are used all over the world. The light blue parts of this world indicates the country confirmed to be using the TRON. And the performance of micro T kernel operating system is proven. The micro T kernel performance proved to perform the best in IEEE authorized third-party paper. The graph on the right shows the time required for task switching and task activation for interrupt with multiple real-time operating systems. Here, the task switching time is shown, and here the task activation for interrupt time is shown. And here, in both context switching and interrupt handling, micro T kernel, which is the red part, clearly outperforms the other. And hence, micro T kernel is proven to perform very well on embedded real-time systems. And not only that, ITRON and T kernel is fast, but it is also a mature technology, having almost 40 years of industrial experience. And it is thus accepted by mission-critical applications, for example, even in artificial satellites and spacecrafts. And Hayabusa is a spaceship from Japan, and it continued to work for 7 years in space. So making a system that continues to work for 7 years is very difficult. But using the TRON operating system helped that in Hayabusa spaceship, which gave us important scientific knowledge back to the Earth. So actually, today we have an expert on space-related computer technologies. So let me pass my microphone to Dr. Hihara. And Dr. Hihara has worked on building reliable artificial satellites and spacecraft using TRON operating systems. So let me pass my microphone and switch to Zoom now. Dr. Hihara, please. Can you switch?
Can you hear me?
Yes.
Okay, let me share my screen.
Yes, we can hear you. Yeah, the slides are visible.
Okay. Okay, thank you very much for inviting me on this great conference. My name is Hiroki Hihara from NEC Space Technologies. I'm involved in the development of onboard computers and routers for satellites. The commercial market for space systems is expanding nowadays, and I would like to talk about how TRON supports dependable space systems. Satellites are identified as sensors and communication relay nodes for the Internet of Things or IoT network. Even though the network size is huge, the system architecture is similar to the IoT system on Earth. Large amount of data is collected and sent to ground stations. However, channel capacities are not sufficient between satellites and ground stations. Therefore, edge node computers on satellites have data processing functions to reduce the data size. The dependability requirement is severe because of the harsh space environment. NEC Space Technologies has supplied onboard equipment worldwide, especially communication equipment. The communication equipment has been supplied for more than 400 satellites in the world, and no major anomalies in orbit has been reported. We have confidence in the product reliabilities. We are using TRON real-time operating system for more than 30 years. And these Asinaro series satellites are epoch-making because all major subsystems employ MikroT kernel real-time operating system. The subsystems are data handling subsystem, attitude and orbit control subsystem, and mission payload subsystem. They are synchronizing by utilizing MikroT kernel real-time operating system. They are commercial satellite, and the first one is still working with no problems for more than 10 years. It has become a social infrastructure now. And MikroT kernel is now incorporated in IEEE 2050-2018 standard. So we are developing new satellite series now, and the real-time operating system will be upgraded to fully comply to the IEEE standard. The TRON real-time operating system has been playing an increasingly vital role in recent years because more and more heterogeneous processing elements are used. Let's take a look at the technology development trend. Makimoto's wave was published in IEEE Computer 10 years ago. It shows 10-year cycles of investment. The cycle of standardization and customization shifts approximately every 10 years. The first one is standard discrete device, and custom LSI came, then memory devices and microprocessors, and then again custom ASICs, and next FPGA, and system on chip or system in package came. And recent 10 years are for heterogeneous processing element. Makimoto-san called it highly flexible super integration in IEEE Computer magazine. Now we have integrated LSIs with microcontrollers, FPGAs, and even AI engines. We use 5-layer architecture to utilize heterogeneous edge node computers. Layer 1 is a device computing layer, and now it is for mainly FPGA. And layer 2 is machine-to-machine or M2M network inside satellite systems. Layer 3 is for conventional microcontrollers, and digital signal processors and neural processor units are also in this layer. And layer 4 is the internet, and layer 5 is for cloud servers. Recently, layer 1 through 3 are integrated on one chip. So software must be synchronized with hardware processors to keep deterministic requirement. IEEE 2050-2018 real-time operating system, and now TRON MikroT kernel real-time operating system enables microcontrollers to synchronize with hardware processors. TRON real-time operating system leverages SoC devices because IEEE 2050-2018 or TRON MikroT kernel realizes deterministic heterogeneous processing element. This slide shows the most successful onboard record. Yashiro sensei talks about the Hayabusa the first version of Hayabusa, and now this is the Hayabusa 2 satellite. This is the asteroid probe. It succeeded automatic and autonomous landing on taking off from asteroid Ryugu, which is 300 million kilometers away. It has proven the dependability of TRON real-time operating system. Thank you very much.
Thank you, Hihara-san. I know it is very difficult to implement a system that works for more than 10 years. So I thank for your hard work on that and also for using the TRON project for such important applications. Thank you.
Thank you very
And
much.
let me thank you. So let me proceed again with my slides. Can I switch? Okay, thank you. And so, for realizing the IoT in reality, we implemented 6-LoWPAN protocol stack for micro T kernel. And for realizing IoT communication necessary for highly functional distributed system, we implement a 6-LoWPAN protocol stack. And 6-LoWPAN is IPv6 over low power wireless personal area networks. And it enables IPv6 communication over resource-constrained embedded nodes with low-power communication protocols like Bluetooth LE, and including simple sensors and actuators. And our 6-LoWPAN protocol stack can realize both consumer electronics control and IoT communication 6-LoWPAN on a single MCU, thus resulting in lower cost and IoT control collaboration made easier. Usually, this kind of thing is often implemented using 2 chips, the one for the real-time operating system and one for the IoT communication, but we allow the unification of such implementations in a single MCU. And we made it very low power and compact. And as the whole system size used by operating system kernel here, and the protocol stack here, and the device drives are only 13 kilobytes of memory, RAM, and 42 kilobytes of ROM, so it can be considered very small. And if usual embedded processors are used, for example, applications can use the rest 80% of the RAM and 92% of the ROM for IoT device development. So applications can use the most of the space that provided in the embedded processors. And for realizing the IoT devices that last for years with common dry cell batteries, power management is very important. And we support beacon mode supported by IEEE 802.15.4 and confirm that the battery of sensor system lasts for 18 months with only 2 AAA batteries. The figure here shows the waveform of power consumption by the device. And power is only consumed at specific intervals that is shown as a peak. And the power is not consumed in the middle of the peaks, so which thus helps us to save the battery life for years. And we also have a 6-LoWPAN border router that connects IoT network and the internet. And we have implemented 6-LoWPAN border router with T-kernel 2.0 and T2EX, thus fast, responsive, and real-time. And the booting time of our 6-LoWPAN border router is less than 0.3 seconds from the SD card. This is the contrast to Linux-based routers that you have in a house, which takes usually more than 30 seconds. And it is equipped with usable management console as shown on the right. And what is important in TRON 6-LoWPAN border router is that it is designed to seamlessly connect the web and the IoT protocol. For doing it, it is equipped with web and the IoT protocol conversion. Usually, the web uses the standard IP like IPv4 or IPv6 in combination of the hypertext transfer protocol HTTPS and its TLS version for security. However, the IoT nodes is a very resource-constrained node, so you cannot speak the standard IP and HTTP directly. Thus, they use 6-LoWPAN and core protocol instead. However, as these protocols are very different, it cannot communicate with each other without the help of some special software. So we decided to have a 6LoWPAN border router with web and IoT protocol conversion that converts HTTP to COAP. And web application using JavaScript, etc., can access IoT devices without any specific gateway. So here, the TRON 6LBR seamlessly connects web and the IoT by doing the IoT protocol conversion. And the integration of web applications and physical IoT devices made easier. And we also provide standardization hardware for the IoT, named IoT Engine. Although designed primarily for the development board, it is small enough to be embedded in final products. And connected here, standardized between MC manufacturers for compatibility. So if we want to change processor to a more high-spec MCU later in development, it is possible by replacing this module. And this is the IoT engine connector standard. And there are several IoT engines sold from multiple vendors with many different microcontrollers available. And some of the IoT engine is based on the ST Micro, Imagination, and Cypress, and Toshiba, and Renesas. And here you can see that the company is not restricted to Japanese companies and are supported by companies from all over the world. And as a whole, we are providing a complete set of IoT framework on the devices using the T-kernel 2.0 series. Edge nodes are implemented using micro T-kernel, and 6LoWPAN protocol stack supports the IoT communication on top of it. And the edge nodes are implemented using micro T-kernel, right? And the 6LoWPAN border router is implemented with T-kernel 2.0 and T2EX, and supports seamless integration of the IoT and the web, realized through the API, not the API, the protocol conversion. And for the cloud servers, we need a mechanism to support intra-device collaboration to realize highly functional distributed system, and it is supported by UCode framework, which we describe from our next slides. And for realizing the context awareness essential for highly functionally distributed system and ubiquitous computing, identification of objects is very important. Please take a look at the figure on the right. This is a context-aware explanation diagram from the early days of TRON. So it's a very old image. And the system needs to handle the information that Bob is here inside. But there are many Bobs in this world, and hence the name Bob is not the best solution to identify him within the computer system as the primary key. So in order to solve this, we defined UCode, which is a world unique identifier associated to individual objects. And this is the structure of UCode identifier. And basically, UCode is a 128-bit world unique identifier, and they can be freely used worldwide under the governance of the upper domains. And by using UCode, all identities related to ubiquitous computing and highly functional distributed system can be handled within computers precisely. However, for handling information like Bob is here in the previous page, data may be distributed in different data sources from different organizations. For example, imagine a situation where we want to let the computer system decide whether to open a door or not, open a window or not, like this. So in order to decide for the computers to open the door or not, we first need to, for example, we need to get the temperature of the outer space, right? If it's 27 degrees, then it might be too hot, so the window can be open. However, we don't want to let the window open unless someone is not inside the house. So we need to fetch the information, for example, from Google Calendar that I am home today. And in addition to that, we also need the weather information because we don't want to let the window open when it's raining hot outside. So here, the context awareness needed for deciding how to act for computers in the IoT requires information from different data sources. So such aggregation of information is not simple, and thus we provide a framework for integrating context information from various sources for context awareness. And our solution is to provide unique U-code distributed database, which is a virtual database over existing data sources existing in real world. So here we have databases, temperature sensors, air conditioners, and the web services like Google Calendar or Open Weather. And in the current situation, we need to fetch information individually from different sources, but what we create is a virtual database that works as a front end for fetching all the information at once. By querying this virtual database, all associated information can be queried at once, which helps realizing the context awareness in highly functionally distributed system. And this is the architectural summary of U-code distributed database. And basically, U-code database works as a thin aggregation layer that delegates data accesses from multiple databases, which is UDF here. And user can access all data from multiple sources within a single query. That's the idea of U-code distributed database. And finally, let me discuss the future of computers that TRON Project pursued. And as explained earlier, the TRON project has been started with a clear vision to realize highly functionally distributed system where all objects around us would have embedded computers inside and collaborate with each other to form an optimal environment, which is now referred to as smart building or smart houses. Here in the slide, you can see intelligent lighting, intelligent seating, and intelligent sensors and walls, and that kind of thing, are all connected to the intelligent object network and collaborate with each other to form an optimal environment. And our vision for the future computer remains still the same, but now we have concrete technology, so we want to use it now. And this is because the computer and communication technology has evolved much in the past 40 years, including the internet, web technologies like REST, GraphQL, and WebSocket, and MQTT. And we also have very rich microcontrollers and very low-power microcontrollers available. And also we have generative AI like ChatGPT, so we need to integrate that into realizing the highly functional distributed system. However, the current situation of IoT in reality is not far from ideal. Although the computer technology today has come close to the ideal of highly functionally distributed system, there are still some gaps that prevents us from realizing the ideal. Today, many IoT-enabled devices are generally available. For example, you can buy IoT-enabled air conditioners from some store, and also panel heater equipped with IoT communication, and also humidifier and circulators. However, the current situation tends to be divided by manufacturer boundaries. For example, if you want to use the IoT functionality of some such IoT-enabled device, it is in general required to install corporation-specific smartphone applications into one's own smartphone. And by doing so, the collaboration of the within Corporation A devices can be realized. However, the different IoT products from different vendors, like Corporation B, is left to be isolated in the IoT network. And this is not what we pursue in highly functionally distributed system, where all the devices forming the environment need to collaborate to form an optimal environment. And that's the idea of highly functional distributed system. So we need to combine it together. And in order to solve this gap, TRON project is working on IoT Aggregator, which is an IoT device API abstraction layer for interoperability across vendors. And it provides the standardized API over devices from different manufacturers with different APIs and functionalities. Even if Corporation's B circulator on the previous page has a totally different API set compared to the corresponding one from the Corporation A. IoT Aggregator works as an abstraction layer and thus standardize the API format to a single, unique, standardized API format. So all devices from different vendors are used similarly by using the IoT Aggregator. And in addition to that, one-stop authentication and authorization is handled across IoT device vendors. And this helps IoT application to utilize IoT devices from different vendors in a single authentication, which is very useful for realizing the IoT system from multiple vendors. And it provides a single endpoint for accessing IoT devices in the environment to support collaboration among intelligent objects in highly functionally distributed system. And the reason why we build IoT aggregator is to build up an ecosystem for the IoT. It can be considered identical to portable phones becoming smartphones that we have now. Portable phones got ecosystem when they evolved from feature phones to smartphones. Before the smartphone, third-party applications could not be released or installed on top of mobile phones. And we now have Uber and that kind of interesting software, but in the old days, the feature phone had already software installed by the manufacturer, so interesting third-party application could not be installed. What smartphone has done was to provide an ecosystem that anyone can join to gain benefit, to release software on top of it, and to use software on top of it. Like smartphones, we are developing a framework on top of existing IoT systems so that not only the hardware vendors, but also any companies, organizations, or individual can install third-party software to smart building environments. So it's like smartphone. So we want to let smart buildings and smart houses to allow installation of third-party software. And this is a framework for smart houses and buildings where third-party software can be installed. And that's our idea. And based on our real-time operating system and IoT aggregated technologies and the idea presented so far, we have built an IoT-enabled university campus where over 5,000 devices are installed. And it is used as our latest testbed for IoT and highly functionally distributed system. And based on the IoT aggregator technology, we are providing the building API service to any member of the faculty, including students and the faculty staffs. And like smartphones, let them create new applications on top of this IoT environment. So this is considered a demonstration experiment on providing an ecosystem for the IoT. We're doing it in the university. And let me show you a demonstration of an IoT product started by the faculty member of this building. And this is a sample system that helps persons on a wheelchair and with visual disabilities.
照明値はオフです。照明値はオンです。ダブルタップでトグル。エアコン画面、データダウンロード完了。電源はオフです。ダブルタップでトグル。電源をオンにしました。27度です。18度、16、30度、30度、ダブルタップで設定。28度、ダブルタップで設定。温度を28にしました。3201教室。3C、廊下。キープさん、エレベータホール。マルキボタン、ダブルタップで呼び出し。下向きボタン、ダブルタップで呼び出し。エレベーターを呼び出しました。
So you may have realized, but this example application is an application for visual impairment. So the user interface it does not use switches and buttons, so that persons with visual disabilities can operate without looking at the screen. So this is a special application for the persons with disabilities. And let me show you, and even undergraduate students try to implement something interesting based on the API provided. And this is an example of senior thesis research to implement a navigation system using Open IoT API and also chatGPT AI, which is a large language model. So he made a navigation system using the LLM.
話しかけることで教室の電気を消したりするなどの機能も備えています。
And when a user specifies a place that he wants to visit, the navigation starts. So the navigation is done by the natural language, supported by the chatGPT API. And using the location service, the guide content is changed according to the current indoor location using the API service. And door is automatically unlocked by approaching the door like this, and also in the laboratory. And he also can turn on and turn off the light using the natural language. Yeah, so this is developed by the undergraduate students. So by opening the API to general public, the third-party persons develop interesting applications. So we are demonstrating that in a university campus. And lastly, we would like to discuss the future of TRON project with you. And first, we would like to thank you all for supporting us for so long, 40 years. 40 years is very long. It's like my life, so it's very long. This has only been done. TRON project has continued for more than 40 years because of the support of the companies, organizations, and individuals that supported our project for so long. And we would like to express our deepest gratitude for all help and contributed to the project. And IEEE has continued to support us long from the early times of TRON project. So, for example, the publication of proceedings in the early days of TRON project, and also promoting our work and publishing MicroT-kernel 2.0 as the IEEE standard. Hihara-san has already explained that, but let me repeat that. And in 2018, MicroT-kernel 2.0 operating system is accepted as the IEEE standard for real-time operating system for small-scale embedded systems. And TRON operating system has long been the de facto standard, and now it is also accepted to be a de jure standard, and we would like to express my gratitude for those who helped us realize the standard, including the IEEE. And from the very beginning of the TRON project, we have continued to hold an annual conference and exhibition called TRON Symposium. TRON Symposium is technically co-sponsored by IEEE CT-SOC, which is here, and TRON Forum is officially a sister society of IEEE CT-SOC. So we are the member of the IEEE. And we welcome your submission of your papers to TRON 25. So it is not limited to papers related to TRON project, but any papers related to the aimed at realizing the future of computers like IoT, AI, and other technologies is welcome. So please submit if you're interested. And let me show you some of the pictures from the TRON Symposium last year. The symposium is a combination of exhibition and conference, just like we have CES and ICC the same time here in Las Vegas. And this is a keynote speech by our leader, Professor Sakamura. And we show the same slides in English as well, and simultaneous translation is available. So non-Japanese speaker is welcome to attend this event to enjoy his speech. And this is a picture from a different session, and also a picture from the exhibition floor. And TRON-related technologies are exhibited. And finally, I would like to discuss on two questions. What do you expect the future of TRON to be? And what do you expect the future of computer technologies to be? Let me pass my microphone to Hihara-san. Hihara-san, what do you expect the future of TRON to be?
Oh, I expect the development system would be centered around language, because we have to assemble many kinds of heterogeneous processing elements, and even though such kind of complexity, the operators are novices of such kind of complex heterogeneous processing element. So the unified development language is very useful to encompass heterogeneous processors. So I would like to expect a development system centered around language.
Okay, thank you. That's a good point. And personally, I would like to expect the TRON project to do new things, continue to do new things, and only keeping the old standards that, as a legacy of TRON project has developed, is not the way TRON project to be. So I myself is developing IoT aggregator, which is new technologies based on the TRON project, and actually developing a new T-kernel-based operating system design with enhanced security that we have never seen. And I would like to always make something new on TRON project, as TRON project always aims at the future. So I would like to do that. And for the audiences here, now it's your turn. And because the TRON project is open to anyone, please remember that. TRON project is open to anyone. You can join TRON project to be by becoming a member of TRON Forum, which is a non-profit organization. So anyone is welcome to join if you're interested in making new computers. And there you can join working groups to discuss standards. So it may be possible to be involved in making the new IoT standard for the IEEE. So you can join that and also implement new operating systems and framework. So let's create the idea of future computers by joining our TRON ecosystem. And let me ask Hihara-san again. Do you have any message to persons now considering attending the TRON project?
Oh, I think TRON project is good for both experts and novices because the performance of the TRON real-time operating system is very good, especially for deterministic systems. So it can synchronize with heterogeneous processing element such as FPGA and dedicated processing ASICs. And also recently we have to incorporate the neural network processor unit. And TRON operating system leverages conventional microprocessors to synchronize with such kind of processors. And in addition to that, the completed educational programs are provided. So novices of the real-time systems can learn such kind of real-time operating systems through TRON operating systems. So I think the TRON project is good for experts and novices. So I'd like to join many people to TRON project.
Thank you very much. I agree on that because TRON project has a very advanced expert on the computer technologies, but also members that are something like a user group of TRON. So we also welcome professionals and we also welcome novices to learn how to use TRON and to give feedback to us. And also, what we provide is a working group of many different sub-projects. And in some working groups, the education working group is set up. So the education working group is aimed at providing the learning materials for TRON operating system. So you can involve in that project, and also you can use that learning materials for your use in the TRON real-time operating system. Okay, so this is a list of TRON project members in 2016. So the white letters here are all the members, so there are many. And there are members from academic institutions and non-profit organizations, governments, and industries, and whatever. There are many members from different organizations and companies. And TRON is a non-profit organization, and we are collaborating with our members to make new specifications, design and implement computer systems, and to deploy our technologies to the general public. I would like to thank the current and past members of the TRON project. I am looking forward to seeing new members for this year, 2025 and onwards. And thank you very much for joining this industry session on TRON project. And now I would like to accept questions from audiences. Are there any?
Anybody have a question? Question for anyone? Let me put one in.
Okay,
so could you talk about some of the cybersecurity features that are part of TRON? I know conventional operating systems have like secure kernels, code-signed applications, protected memory spaces. What are the security features of TRON?
Okay, let me go back to the slide.
Yeah.
This okay. Okay, so T2EX provides this memory protection mechanism, and that can be used to realize higher the level of memory protection on embedded systems. And also, in the old days, we had micro T-kernel ring protection mechanism and that kind of thing. And we're developing new secure kernels that is different from any other embedded devices. And I would like to release that in the upcoming ICCE, maybe. Thank you.
Okay. Thank you very much. Very interesting talk. Thank you for organizing this industrial program. I'm Funabiki. I send a message to you. Thank you very much. So, as a teacher in the university, I assigned some projects related to IoT systems. Then I think for students, they are usually using like a Raspberry Pi or Arduino as a device. So is it possible to install the TRON to these devices easily?
Yes, we have implementation of a micro T kernel for micro T kernel 3.0 for Arduino R for Wi-Fi. So we can install TRON operating system on top of that to realize real-timeness in such devices. And however, the current situation is that it is not available in the Arduino IDE. So we're trying to implement that now.
Also, how about device drivers? Because sometimes we have to use several different like sensors or.
Yeah, many of the device drivers are provided, including the Wi-Fi currently.
Yeah. Wi-Fi. How about the sorry, it's very specific. How about the SAN?
SAN is not supported currently, but if you give me comment, maybe.
Because it also comes from Japan.
Okay, we want to implement that later.
Yeah. The last question is how about program languages?
Available languages.
Yeah, like Python, C, or other major languages.
Basically, we use C language, but also we have implemented micro Python and that kind of environment on top of a micro T kernel. So you can program in Python and Ruby and that kind of scripting language is also available. And also we can use Rust for increased security.
Okay. Yeah, thank you very much.
Thank you very much.
Other questions? Comments?
Thank you very much. Very interesting and impressive for me. Yeah, you introduced some use cases in smart home and smart building and so on. Mm-hmm. So how the TRON play an important role in, for example, the edge computing or edge mobility scene and so on, maybe autonomous driving and so on. Would also require some real-time behavior. Do you have some projects or activities in such a situation?
Yeah, because the TRON real-time operating system is primarily implemented for embedded devices, mission-critical embedded devices like the automobiles. So we're trying to implement IoT functionality over these systems so that the automobiles and that kind of IoT systems can be implemented.
Okay, very impressive. Thank you so much.
Thank you very much.
Other comments, questions?
Thank you so much. Very interesting talk. Since TRON is so portable and very lightweight, how do you see the future of TRON being implemented in, let's say, non-traditional applications, specifically smart sensor nodes? The reason I'm asking is that we are a small company from Germany. We are developing a new kind of universal sensor chips that's supposed to cover a very large array of applications. And actually, having learned about TRON today, it's a perfect candidate for being integrated directly on silicon for these universal type of sensors. So do you see this, let's say, application into more hardware fitting with the vision and the philosophy of the TRON project and the TRON Foundation?
Okay, so could you repeat that question again?
So do you feel that implementing TRON near the hardware, non-traditional hardware, so not on FPGAs, not on microcontrollers, but full custom mixed signal chips, would that be fitting with the vision and philosophy of the TRON project?
Of course, it is a perfect fit because microkernel operating system provides source code which is very portable, and you can re-implement the hardware-specific part to adopt the new hardware. So it is possible, and it is also welcome. So you're invited to the TRON program. Thank you.
Other questions? Well, I'll throw one. I was intrigued by one of the slides you had, where I think you showed. I think you called it Business TRON or BTRON, where you had the operating system associated with a laptop computer or notebook computer, that sort of thing. Yeah, I was aware of TRON and embedded applications. This was completely new to me. Are there any commercial products on the market today that actually are in this format of a desktop or notebook computer?
Yes, actually, it is a very old implementation, but the commercial product of BTRON operating system is sold from Personal Media Corporation, and there's still some fans that uses the BTRON operating system daily. And this is actually a screenshot from the BTRON operating system. Now works in the VMware workstation, so you can use a BTRON now, actually.
Thank you.
Thank you very much.
More questions, comments? We have a few more minutes before we move to the next. Yeah, you're going to make me run. We need a different shape room.
Very interesting set of projects you showed and applications. Specifically, I'm more referring to the applications for disability applications, where how do you enable for as a platform and ensuring also that the whole ecosystem is accessible both for application developers and as well as for users. Have you developed the resources?
Could you repeat that question again?
Yeah. Have you developed the resources to make it more enable or develop more as a platform instead of just singling out one single disability? But have you looked into developing this as a platform for a lot of disability-focused applications within your university?
Yeah, we're doing the Enableware conference annually, and we're developing the Enableware for visually impaired persons and also person with wheelchairs and elderly persons, and also for deaf persons. So we're implementing Enableware for different persons with different disabilities, and we're trying to integrate that into a single unique specification of Enableware.
Thank you. Very impressive. Yeah.
Thank you very much.
Still have time for just a few more questions. We have another 5 minutes before we move to the next session. Any other comments or questions? Just raise your hand. I'm getting my exercise today.
Again, my question is about educations. So if I want to ask the educated students to use a TRON system. What is your recommendation? So just access the website or sometimes take a seminars in your university or read the books or whatever.
Okay.
Let us know.
I would recommend to the university to join the TRON Forum because TRON Forum provides the learning materials for members. So academic members, I think, are free of charge in attending. So I would suggest attend the university who wants to teach TRON, the TRON Forum, to get the learning materials. And also we also have the website for learning materials, so you can use that.
So TRON Forum is every year, December, second week of December, I think.
TRON Forum is a organization, so you can join. Just join. The TRON Forum provides a TRON show, which is a exhibition.
I see.
But the TRON Forum is an organization, so anytime you can join.
So what we can do if we join?
Please visit the TRON Forum website and look for admission information.
Okay. Yes.
I will let you show that later. Okay.
I think we got one more minute left if somebody wants to squeeze in a quick question or comment. Otherwise, I think we can thank thank our speaker for this incredible presentation.
Thank you very much.
Thank you so much.
Thank you very much, Hihara-san.
You want to switch to the open slide there?
Thank you very much.
Okay. Oh, I think we're going to switch to the awards program, right? Yeah. Okay.